It's now time to algebraically determine the model parameter that minimizes mean squared error for the constant model in particular. Now, when we were looking at that toy data set in the last video, where our y values are 20, 21, 22, 29, and 33, it seemed like the value of theta that minimized mean square error for the constant model was 25. We didn't explicitly state this in the last video, but 25 is the mean of these 5 values. And it turns out that this relationship holds true in general. The mean, or average, of our y values minimizes mean squared error for the constant model. That wasn't just a fluke, it always holds true for the constant model. And so what we're going to do in this video is prove that fact using 2 different algebraic methods. One way we will do this is by using calculus, and another will employ a nice little algebraic trick that we will see again in the future. Now, the slides here have all of these steps written out, but for the purposes of this video, I will work out all of the steps on the iPad, and you can refer to the slides as you need to as a reference in the future. So, going to the iPad, our average loss, or empirical risk, looks like this. It's 1 over n times the sum of yi minus theta squared, where our sum is over all n of our data points. Now, from calculus, we know that in order to minimize a function with respect to some variable, to do that, you take the derivative of the function with respect to that variable and set that equal to 0 and solve for the minimizing value of that variable. So what we want to do here is take the derivative of our average loss with respect to theta and set that equal to 0. Since our average loss is a sum of all of these individual pieces, we know that the derivative of our average loss will also be a sum of a bunch of derivatives. So it might help us to step aside for a second and determine the derivative of the loss for a single point or a single observation in our data set, because once we know what this single derivative is, we can sort of just substitute that into our average loss expression, and we have the derivative of our average loss. So, the loss for a single point is yi minus theta squared, since we're using squared loss. And the derivative of this with respect to theta, using the chain rule, is 2 times yi minus theta times -1, since the coefficient on theta is -1, which is just -2 times yi minus theta. Now this is the derivative of our loss for a single point, and so what we can now do is substitute this in to the derivative of our average loss. So the derivative of our average loss is 1 over n times the sum for our entire data set of the derivative of all of these individual losses for each data point, and we just computed this to be -2 times yi minus theta, and so I can substitute that in here. And now this right here is the derivative of my average loss with respect to theta. And what I now need to do is set this equal to 0 and solve for the theta that minimizes my average loss. Before setting it equal to 0, what I'm going to do is just slightly rewrite this, because I can pull out the constant of -2 out front. So I can write this as -2 over n times the sum of I going from 1 to n of yi minus theta. And so now what I need to do is setting this to 0. I have -2 over n times the sum is 0. What I can do is multiply both sides by -1 and then by n over 2 to get rid of this quantity. And so what this implies is that the sum of yi minus theta without the constant out front is still equal to 0. And we can continue this on the next slide. What I can do now is use the properties of summations to expand out the left-hand side. So I can write this as the sum of yi minus the sum of theta is equal to 0. Now, you notice theta doesn't involve an I in it. And so what we're doing here is just adding a constant to itself n times. So this really just looks like theta plus so on and so forth plus theta n times, which is just n times theta. And so I can rewrite the second term here as n times theta, and this is still equal to 0. Now if I add n theta to both sides, I get that the sum of my yi's is equal to n times theta. And so now, to isolate for theta, all I need to do is divide both sides by n. So I get that theta is equal to the sum of my i's, or the sum of my yi's, I should say, divided by n, which you will notice is just the mean of y. Since this is the value of theta that minimizes my empirical risk or average loss, this is theta hat. And so we've now proved that for the constant model, and when our loss function is squared loss, the mean minimizes average loss. But wait, we're actually not 100% done yet, because we sort of took the derivative and set it equal to 0 and solved for the value that made the derivative 0. But you may remember from calculus that this value of theta could possibly be a maximum, right? We didn't do the second derivative test to ensure that this was indeed a minimum. And so we can do that because conveniently over here, we have the second derivative, we have the derivative of our average loss with respect to theta. And so what we need to do to be thorough is take the derivative of this again with respect to theta and ensure that it's positive. Because if the second derivative is positive, that means our function is concave opening up at this point. And so the optimal point that we found is indeed a minimum. And so the derivative, and so I'll just title this slide, second derivative test. And so the derivative of our average loss with respect to theta is minus 2 over n times the sum of yi minus theta. What we now need to do is take the derivative of this with respect to theta. And so, again, we can take the derivative of one of these individual pieces with respect to theta and then sub that in, because we know the derivative of a sum is a sum of derivatives. And so the derivative with respect to theta of yi minus theta is just negative 1. Right? Yi is a constant with respect to theta. And so the second derivative of our average loss with respect to theta is still minus 2 over n, but now times the sum of I going from 1 to n of negative 1. This simplifies to 2, which is indeed greater than 0, which tells us our function is concave opening up, meaning that the optimal value that we just found indeed minimizes our average loss instead of maximizes it. So that is the first of 2 proofs that we will look at that shows that the mean minimizes mean squared error for the constant model. Now, I walked through all of these steps in great detail, and there was a good reason for that. It's because you need to know how to reproduce these steps on your own, but for when we also change what our loss function is and for when we change what our model is. So this type of calculus, taking derivatives, setting them equal to 0, and playing with sums is something you need to know how to do, and that's why we had you work on properties of summations in homework 1, so that you were familiar with this type of exercise.